Hey physics kids, this is Mr. Galoya coming at you again. Hey, in our first video we talked a little bit about what are vectors and scalars. I gave you a few examples. We discussed adding up vectors that were along the same grid line. That would be colinear vectors. And we also talked a little bit about adding up perpendicular vectors. In today's lesson we really want to do what's called the opposite thing. Instead of creating one vector from two, we want to take a vector and break it up into its parts. Those parts are called the components, and I'm going to be using my notes and giving you a few examples. So let's get started. So these are the notes that I'm kind of using for video 2, and again, this concept is called vector resolution, and we're basically just taking one vector and creating then two vectors from that one vector, and those two vectors are called components. So the idea is we have this one vector, and we're going to create the two parts from this one vector, and the two parts are going to be then one part will be along the x-axis and one part will be along the y-axis. So we have this vector. We can really think of that vector as a hypotenuse, and we can then draw the components. One vector then that's going to act along the x-axis, and one vector that acts along the y-axis. So in this case we have a plane traveling at 200 miles per hour, and it's traveling then at an angle 40 degrees north of west. So if we put in our compass headings, we have east, north, west, and south. So we can think of that at angles 140 degrees from the x-axis, or we can think of that angle as 40 degrees from the west or from the negative axis going up. So notice we've created then a vector triangle here, and we really want to get this x vector, we want to get this y vector, or in this case we want to get the westerly vector and then the northerly vector. So maybe the plane is traveling it's traveling west, and then maybe we have a wind that's pushing it north, and we have then a combined speed of 200 miles per hour. So here's kind of what we do here. To find this x vector, or to find the west vector, it's going to be really along the negative x-axis. We take the hypotenuse, which in this case again is 200 miles per hour. So we take our 200 miles per hour, and we're going to take this times in the cosine of that angle. When we do that on our calculator, we get 153.2. That'd be in miles per hour. Now this is really acting along the negative x-axis. If we had put in 200 miles per hour times the cosine of 140, we would have got the same number, but it would have been negative. So if we do it this first method, we can put in the negative sign manually, or what we could say is that the plane is traveling west at 153.2 miles per hour. Or we could call that just a negative 153.2. Now to get then the y vector, we'll do the same thing, but we'll do a sine 40. Okay, so we're going to do it the same way in our calculator, except we want to do the sine 40. So on my calculator, I'll take then 200 times sine of 40. Now when you're using your calculator, you want to make sure it's in degrees and not in radians, okay? And so that's going to be 128 point, around 0.6. Again, that'll be in miles per hour. Now notice that's going upward. Would be a positive idea, right? Positive, since we're going along the positive y-axis. Or we could say that's 128.6 miles per hour north. So really what we have here then is we have one vector that's acting along the negative x-axis, 153.2, and then this vector here, the northerly vector, is 128.6. So we have these two, really we've created then the two perpendicular legs of this triangle. And we know then the hypotenuse is 200 because that was given to us. If we want to check our work, we could use, again, Pythagorean theorem. We can square this, and it should be approximately equal to 200. We had to round these numbers. So if we use, to check our work, if you want to use your Pythagorean theorem, we could square that and square this. Again, add them up and take the square root. We should get about 200 from that. Let me check my work here real quick. Yeah, that equals about 200. So we know we're doing it right, so it's always good to have a way of checking our work if possible. I'm going to go to the second example here. Let's say you normally run 5 miles in a direct path to your favorite McDonald's. So that's the hypotenuse, 5 miles. Let's say one day you decide to vary your route by running the legs of the right triangle formed instead. How far do you run now? So what we're doing is we're really running here, and then we're running here. In both ways we can run, we still get to McDonald's, right? In this case, we're running the legs of the triangle. In this case, we're running the hypotenuse. So this would be our x-axis. This would be our y vector, our x component and our y component. So again, to get the x component, we would take our hypotenuse, 5 miles, times in the cosine of 30. To get our y component, we would take our hypotenuse times the sine of 30. Okay, again, we can do that on our calculator. So 5 times the cosine of 30. It's going to be around 4.33 miles. And if we take the sine of 30 times 5, we get then 2.5. So if we want to know how far we run now, we can just add these two numbers up. 6.83. So we're running, if we run along the legs of that right triangle, we've run 6.83 miles. If we run the hypotenuse, we run 5 miles. Again, we can check our work by using Pythagorean theorem. Let's do our third example here. Vector resolution, or finding the components of vectors, it's a pretty common thing to do with projectile motion. Projectile motion is an example of a two-dimensional type of motion. We have motion occurring in two directions, really, or 2 dimensions simultaneously. And we see this a lot in sports. And so maybe, for example, we're doing soccer here. We've got the ball on the ground. So maybe we have the soccer ball on the ground, and we have maybe a free kick. The soccer player's kicking it. We get this parabolic type of motion, and we'll study that when we get into projectiles. So what we have then is an initial velocity. In this case it's 20 meters per second. And we have then the angle. That would be our initial theta. Let's say that's 70 degrees. So the ball is traveling with a velocity that really represents the hypotenuse of then a vector triangle. So we have a 70-degree angle at 20 meters per second. So we have a velocity in the x direction. That's an initial velocity. We could call that VXO or VOX, initial velocity in the x direction, or VIX or VOX. And we also have then an initial velocity in the y direction. We'll find out that this is going to be somewhat important to do with projectiles, because we can look at horizontal motion and we can look at vertical motion, and we can look at these two motions independently. Even though the ball is really traveling along the hypotenuse and traveling this trajectory, we can find how far it goes or how high it goes by breaking that initial velocity up into these two components. So again, the Vx would be 20 meters per second times then the cosine of 70. The Vy is going to be 20 meters per second times the sine of 70. Take the 20 meters times the cosine of 70. It's about 6.84 meters per second. If we take the sine of 70 times 20, or 20 times the sine of 70, we get about 18.79 meters per second. We'll find out then when we deal with projectiles, we're going to be using that x velocity to determine then how far forward that soccer ball goes. That would be considered the range, and we can look at the altitude, or how high that soccer ball goes, by looking at the y velocity. Again, these are what are called the components of that original sort of vector. You can basically find the components of velocity vectors. We could also use then displacement vectors. We could also deal with forces, or any sort of vector sort of idea. We can break up those vectors into the two parts. Again, the two parts are called the components. All right, we'll talk to you later. Bye.